Well, it got cut off there, overestimated the capacity of the memory card. Used up more than I thought I was going to use up. Okay. Again, on the radius 10 circle, we know that the coordinates are of the clock positions are all 0, 5, 9, or 10, or the negatives of those numbers. On a unit circle, correspondingly, well, unit circle has radius 1, radius 10 circle has radius 10. They're going to be a tenth as great, so they're going to be 0.1, so 0, 0.5, 0.9, or 1. Okay, so for example, here, this point would be 1, 0. And that would be at arc length 0. Okay, so we come up here, we know then that that's going to be approximately 0.9, 0.5. 0.5 is actually exact, the 0.9 is approximate. And that's at an arc distance of pi over 6. At an arc distance of 2 pi over 6, because arc distance is always measured from this axis, it's going to be 0.5, 0.9. That's at 2 pi over 6, which is of course the same as pi over 3. At 3 pi over 6, we're going to be all the way up to 1. The y coordinate will be 1, the x coordinate will be 0. So that'll be 0, 1 at 3 pi over 6, which of course reduces to pi over 2. And as I said, I recommend you count in multiples of pi over 6, 1 pi over 6, 2 pi over 6, all the way up to 11 pi over 6, and maybe 12 pi over 6. And then you can reduce after you write the multiple of pi over 6. It's very easy to do that. Okay, so we know what the arc lengths are here. And we're going to use the arc distance on a unit circle. This only applies to the unit circle. We're going to call that theta. And of course, theta is a symbol we typically use for angles, because as we said, this arc distance is as good a measure of angle as degrees. And for the purposes of analyzing trigonometric functions, okay, trigonometric functions that you graph, it's far superior because the expression for the rate of change of the sine function is much simpler if you're measuring theta in terms of this arc length. And there's another name for this, it's called radians. Okay, so our radians is defined. It's confusing. I remember being confused by it. It took a while to get my head around it because I was so used to degrees. So I'm going to talk about it in terms of arc length, but that's what radians are. Arc length on a unit circle. Okay, anyhow, our definition then of sine theta and cosine theta is if x and y are the coordinates of the point on the unit circle corresponding to arc distance theta, then sine of theta is y, cosine of theta is x. So, for this point, the arc distance is pi over 6. So we say that the sine of pi over 6 is, well, the y coordinate of this point. That would be 0.5. The cosine of pi over 6 would be the x coordinate of this point, which would be 0.9. There's our definition of sines and cosines. And at this point, you'll be well equipped to just make a table of sine and cosine using these angles and sketch a graph. And I don't think you'll have any trouble doing that given what we did previously. Okay, now we went on and did coin flips. And we flipped 70 coins. I flipped coins and got these results. The class flipped coins and got these results. So when I flipped to get this result in the second row in the second column, the class got the one in the second row, second column. So on this flip, I got heads, and the class at the same time got heads. Okay? And so forth. So that's what this table means. We have 70 flips, 35 on this side, 35 on this side, and as I say, they correspond. My flip at any position here corresponds to your flip at the same position on your part of the graph. Okay? Now we started out just by flipping 2 coins. I flipped a coin and one of the students flipped a coin. We got this. And we saw that we got 2 heads twice. We got 2 tails 3 times. Just look, there's tails, 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 3 times. We got 1 of each 3 times. Okay, so looking at this, it seems entirely plausible that there are 3 things that can happen. You get 2 heads, you get 2 tails, you get 1 of each, and it looks like they occur more or less the same number of times. However, there's another way to interpret it, where we break down how we got the 1 of each. Notice that in one case where we got a head and a tail, it was head first, tail second, and it was done by different people. You know, I did this one and somebody did this one. Okay, and tail head actually occurred once, twice. So now we see that 2 heads can occur 2 times, 2 tails can occur 3 times, head tails occurs 1 time, tails head occurs 2 times. It looks like you get an average of 2, and you can't really tell which one is supposed to be occurring more frequently. So what we did was we went ahead and did a lot of flips. Okay, and now we're going to look at what the results are. Okay, on 5 flips. Now what I did, we have 5 flips. I'll just take this row of flips because these things are all random. They're coin flips. Okay, 5 flips here, and we have 2 tails and 3 heads. So we have 2 tails. So in 5 flips, there are 7 ways to get 2 tails. This is the first one. Then there's another one here and another one here, and throughout. If we take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 series of 5 flips, and they're independent series because you can see that they're independent. 7 times out of 14 we got 2 tails. 5 times out of 14 we got 3 tails, and you can count here and verify whether I did that right or not. 2 times we got 1 tail. There was no instance where we got no tails or all tails, and no instance where we even got 4 tails on 5 flips. Okay? So we can make a histogram. Everybody knows how to do that. We have the number of tails, 0, 1, 2, 3, 4, 5, and each bar here represents the number of times that one occurred. So we have this, this, and this. Okay? And as we might expect, or as experience might develop, toward the middle of the distribution we have more occurrences. Now, for 4 flips, it turns out we got a completely symmetric distribution that looks like this. To get 4 flips, I just threw away this part of the table and just looked at the column of 4 here. 4 here, 4 here, 4 here. And I found that we got no tails once, we got 4 tails once. We got 1 tail twice, we got 3 tails twice, and we got 2 tails 5 times. So there's a pretty classic looking distribution. And it turns out that we can then sketch a bell-shaped curve to fit this distribution pretty well. In the sense that if we made a trapezoidal graph for this distribution and used trapezoids along here, it might well come out very much like what we have here. Okay. Now we also guessed how many heads we would get, and that was before we did any counting. Okay? Now, everybody understands that if the coin is fair, and it's not really fair because you have heads on one side, tails on the other, so one side's going to be a little heavier than the other, and it's going to tend to come up heavy side down. But there isn't much difference in these coins. So the coin isn't quite fair, meaning it doesn't come up heads as at the same rate that it comes up tails, but the difference will be very slight, and for this many flips we're not going to be able to detect that difference. Okay, so our expected number of heads is 35, but we don't necessarily expect that that's what we're really going to get, because These things are random. But we're pretty sure we're not going to get 60 or 70 heads in a row. Okay, and we're pretty sure we're not going to get 70 tails in a row. That would be very unlikely. So getting 35, we kind of expect is going to be more likely than getting 34 or 36, which would be more likely than getting 33 or 37. Okay, so we kind of expect 35. It turns out if we count, we got 39. Okay, well, that's not too unusual. You know, if a couple of flips came out, well, I mean, it's due to the randomness, that's not an unusual result. Okay, now, big point is that if you do these histograms, and let's say we have 1,000 people, and each of them does 1,000 flips, and we, count how many heads, how many times 500 heads came up, how many times 501 came up, how many times 499 came up, we get a picture like this, but it probably looked more like this. Lots and lots of bars, okay? But if we go too far away, the bars are going to get really low, so we can't even see how high they are because they're so low that they're almost invisible. Okay, so the graph like this one for a large number of flips might end up like this. We do a large number of flips, a huge number of times. We're going to tend to get something like this. And the more flips we do, and the more trials we do with those flips, the closer this thing is going to come to what we call the normal distribution, which has this formula, but I think maybe we need a sigma under the square root of 2 pi. I haven't stopped to think about it. I can figure it out, or I could look it up, but I want to figure it out. So I think I'm missing a sigma under the square root there. Okay, so that's how the normal distribution comes from the distribution of like the number of heads we get on a large number of flips. And it's a limiting thing, just like the area of a curve is the limiting value of the area of the trapezoidal approximations as your partitions shrink down. As the intervals in your partitions shrink down. Normal curve is a limit of what we get as we approach an infinite number of bars on the graph. And for 1,000 graphs, I think 476, I think the standard deviation's around 8, so 3 standard deviations below to 3 standard deviations above. That might not be a bad picture of the normal distribution we get for 1,000 flips. Okay, now, we looked at composite functions. People had very little trouble with it, so I'm not going to say too much. If f of x equals x squared, then f of 7, well, 7 has replaced x, so we'd better replace this x by 7, and we get 7 squared, which of course is 49. Okay, and similarly, so we get down to this kind of silly thing where we do f of a stick figure, and it's a square of a stick figure. Because we've replaced x by a stick figure, we better replace this x by a stick figure. And we don't know what stick figure squared means unless a stick figure is some kind of a symbol that has some numerical value that we could square. Okay, and f of aardvark, to pick the first letter in the dictionary and word I use, is just aardvark squared. Again, if aardvark is a variable and has a value, we could figure this out. If it's just a word, we can't square a word. Not any way that I know. Okay, now f of x plus delta x is quantity x plus delta x squared, and everybody wrote it down that way, which is wonderful because what I usually see is a lot of x squared plus delta x, or even x squared plus delta x squared. That's not what it is. Quantity x plus delta x squared, which if you have had some algebra, is x squared plus 2x delta x plus delta x squared, not x squared plus delta x squared. Okay, f of 2 to the x is 2 to the x quantity squared. And of course we simplify that. That's 2 to the x times 2 to the x. By laws of exponents, that's 2 to the x plus x, which is 2 to the 2x. And there's another law of exponents. We just multiply these exponents, we get 2x. Okay. F of 1 over x is the quantity 1 over x squared, we've got to be a little careful here. We've got to say, okay, but x can't be 0, because of course if x is 0, 1 over x isn't even defined, so we can't even do this. We can't even get to this. So we could say that it's 1 over x quantity squared, provided x is in the domain of the 1 over x function. And of course we could say so that f of x, 1 over x is 1 over x squared, since that's what we get if you square 1 over x. Again, you got to specify x not equal to 0. Okay, f of square root of x is the square of the square root of x. Now most people wrote down just x for this and didn't put any qualifiers in. There needs to be a qualifier because x can't be a negative number, or we don't even get to start, because you can't do the square root of a negative number. So we got to say that x has to be greater than or equal to 0 because of this expression. Even though if you square the square root of x, you get something that looks like x, it's not true if x is negative. You can check that out. Well, you can't even do the square root of a negative, so it doesn't even make sense. So we could say that f of square root of x equals x, yeah, but only if x is greater than or equal to 0. Okay? And f of g of x is what? Well, we've replaced x by g of x, so it's going to be g of x squared. We've got to replace this x by g of x. And then this says, for all x such that g of x is defined. Okay? And I introduced a couple of symbols. The upside down A means for all, and the thing here means such that. And this is called a universal quantifier. And there's also an exponential, I want to say exponential, exponential qualifier, means it exists, existential quantifier, meaning there exists. So those are important symbols that you should know. You're going to see them if you take any significant amount of mathematics in college. Okay, then we move on to the difference quotient, and the difference quotient is incredibly important. And we had a lot of trouble with some of this notation, and especially with being able to see these things on the graph. So I'm going to stop here and pick up again.